Section 5.1, area of a general region. In this section, we study how to compute the area of a general region. Here, we have some examples about how people compute the area of a region. Example 1, we have a rectangle. The formula to compute the area of a rectangle is simple. It is base times height. Example 2. Now we have a parallelogram. What is the area of a parallelogram? It turns out that it is still base times height. But why? If we cut the parallelogram along this vertical line and move this part here, then we will have a rectangle. So therefore, area of a parallelogram is still base times height. Example 3. Now we have a triangle. It is well known that the area formula for a triangle is 1/2 times base times height. But why? Let me make this triangle into a parallelogram. Through this top point, I draw a line parallel to the base of the triangle. And through this base point, I draw a line parallel to this edge. Then I have a parallelogram. The area of this parallelogram is base times height. This parallelogram consists of two triangles. So therefore, area of this triangle is 1/2 of the area of the parallelogram. And therefore, we have this area formula for a triangle. Example number 4. Now we have a polygon. How to compute the area of this polygon? One simple idea is cut the polygon into triangles. We know how to compute the area of one triangle, right? So I compute the area of each triangle. Then make a sum of the areas of all the triangles. The sum is the area of the polygon. Example number 5. In all the above examples, the regions are quite simple. Why I say that? The regions in example 1 to example 4, they are simple regions because those regions, their boundaries consist of straight lines. So for the area of a simple region, easy to compute the area. Just cut the simple region into triangles. Then we can get the area of that simple region. Now, a lecture question is how to exactly find the area of a general region. By a general region, I mean the region, its boundary is a curve. It's a curve. Here we have a general region. The boundary is a curve. Now the question is how to exactly find the area of this region. Now this time we have to use a limit. We can approximate the general region by a polygon. Graphically, we can see that when the number of the edges of the polygon is large, the approximation of the general region by this polygon, the approximation is good. It's a good. Okay, now I use a limit to find the area of the general region. I increase the number of the edges of this polygon to infinity. Then the area of this polygon will approach some number. The number is the area of this general region. Now, more examples below, okay, in the following, more examples about how to find area of a general region. Example 1. Find the area of the region bounded by this parabola and the x-axis on the interval 0 to 1. The region is denoted by S, and the area of the region is denoted by A. We want to find A. The region in this example is the shaded region in this diagram. It lies between the parabola x squared and the x-axis, and between 0 and 1. This region is a general region, not a simple region, because the top boundary is a curve, a parabola. It is not a straight line. If the top boundary is a straight line, the region is just a triangle. Its area is easy to tell. But now, S is not a triangle because the top boundary is a curve. Now, how to find the area of this region? We can use polygon to approximate the region, but in this example, we use rectangles to approximate the region. The area of a rectangle is more straightforward to compute than the area of a polygon. As a first step, let me use two triangles to approximate the region S. Between 0 and 1, I pick the midpoint 1/2 and use 1/2 to cut the interval 0 to 1 into two subintervals. The first subinterval is 0 to 1/2, and the second subinterval is 1/2 to 1. Now, based on each subinterval, I build one rectangle. Over the first subinterval, I use the function value. The function is x squared. The function value at the right end point, 1/2, as the height to build one rectangle. And on the second subinterval, again, I use the function value at the right end point as the height to build one rectangle. Now, let me compute the area of each of these two rectangles. The first rectangle area is base times height. Base is 1/2. Height, function value at 1/2. It is a 1/2 square. So base times height. This number is the area of the first rectangle. Now, area of the second rectangle is base 1/2 times height, function value at 1. So this number is area of the second rectangle. Now make a sum of these two areas. Then we get 0.625. From this diagram, the area of the region clearly is less than the sum of the areas of these two triangles. Therefore, we get this inequality. A, we want to find A. A means the area of the region S. From this diagram, we can see that A is less than 0.625. Okay, at this point, we don't know what is A, but I can tell you that A is not greater than this number. Similarly, we can find a number below A. Now this time, let me erase these two rectangles. Okay, now build a second pair of rectangles. Now this time, over the first subinterval, let me use function value at the left end point as the height to build one rectangle. Function value at 0, function is x squared. Function value at 0 is 0. So this rectangle, the height is 0. Over the second subinterval, I use function value at the left end point, 1/2, as the height to build a rectangle. Now, compute areas of these two rectangles. Area of the first rectangle, the height is 0, so area is 0. Area of the second rectangle is a base, 1/2, times height, function value at 1/2. 1/2 square function value. So this number is area of this rectangle. Now make a sum. Then we get 0.125. From this diagram, we can see that the region, the area of the region clearly greater than the sum of the areas of these two rectangles. So we get A greater than 0.125. At this point, I don't know what is A. I want to find A. I don't know what is A, but I can tell you that A lies between these two numbers. A greater than 0.125 and less than 0.625. This is the first step. I use only two rectangles. Then I can tell these two, I can tell a lower bound and upper bound for A. Now in the following, I use more rectangles to improve the lower bound and upper bound. In step 1, I use only two rectangles to approximate the region S. And I got the area of the region was less than this number and greater than this number. Let me call this number an upper bound for the area A, and this number a lower bound for A. Now, in step 2, I use 4 rectangles to approximate the region S, and we will see that we can have a better upper bound and a better lower bound for A. Now, step 2. Okay, step 2. I use 4 rectangles to approximate the region S. I cut the interval 0 to 1 evenly cut into 4 subintervals. The cutting points are 1/4, 2/4, 3/4. Now we have 4 subintervals. Over each subinterval, build 1 rectangle. Over the first subinterval, let me use the function value at the right end point to build a rectangle. Its area is base, 1/4, height, function value at 1/4. So this number, base times height, is area of the first rectangle. Similarly, over the second subinterval, use function value at the right endpoint as the height to build a rectangle. Area is base 1/4. Yeah, base, the length from the distance between these 2 points is 1/4. So base 1/4 times height, function value at 2/4. 2/4 square. Function is x squared. So this number is area of the second rectangle. And similarly, the rectangle use function value at the right endpoint to build that rectangle. The fourth rectangle use function value at the right endpoint to build that rectangle. And the corresponding areas are these 2 numbers. Now, make a sum of these 4 areas, then we get the sum is this number. According to the book, because we use right endpoint to build rectangle, so the notation for this sum is arrow. Arrow means right endpoint. 4, arrow 4. 4 is the number of rectangles. 4 rectangles. So arrow 4 is the sum of areas of these 4 rectangles. From this diagram, we can see that the region S lies below the 4 rectangles. Therefore, the area of S is less than the sum of the areas of the 4 rectangles. Therefore, we have this inequality. A is less than this number. This is an upper bound for A. Compared to the upper bound in step 1. Upper bound in step 1 is 0.6. As I remember, it is 0.625. So this upper bound is closer to A than the upper bound in step 1. Step 1, I only use 2 rectangles to approximate the region. Now I use 4 rectangles, so I can get a better upper bound. Now for a lower bound, I erase these 4 rectangles. Then rebuild rectangles. Now this time, I use function values at left endpoints to build rectangles. Over the first subinterval, use function value at left endpoint, 0. Function value at 0 is 0 as height to build a rectangle. Yeah, the area is 0 because the height is 0. Area is 0. Over the second subinterval, use function value at left endpoint, 1/4, as height to build 1 rectangle. Area is base, 1/4, times function value. Yeah, this number is area of this rectangle. Similarly, over the third subinterval, use function value at left endpoint as height to build a rectangle. Area is this number. And for the fourth subinterval, use function value at left endpoint to build rectangle. Area is this number. Now make a sum of these 4 areas, then we get this number. The notation for this sum is L2. L means use function value at the left endpoint to build rectangle. L, left endpoint. 4. This number 4 is the number of rectangles, 4 rectangles. From this diagram, the region S clearly lies above the 4 rectangles. Therefore, area of the region A greater than the sum of the areas of these 4 rectangles. That means they're greater than this number, greater than this number. Yeah, this number is a new lower bound for A. The lower bound in step 1, let me see the lower bound in step 1, is 0.125. Now the lower bound in step 2 is 0.21A75. This number closer to A because I use more rectangles to approximate the region. Combine this inequality and this inequality, then we get these 2 inequalities. Yeah. Even though at this point I don't know what is A, I want to exactly find A, but I can tell you that A lies between these 2 numbers. Now, in the following, I continue to improve the upper bound and the lower bound. In step 2, I use 4 rectangles to approximate the region S. And I got the area of the region lies between these 2 numbers. These 2 numbers can be further improved if I pick more rectangles, if I increase the number of rectangles to approximate the region. Now, in step 3, I use 8 rectangles to approximate the region. When I use 8 rectangles to approximate the region S, then I get a new and better upper bound for A and a new and better lower bound for A. These 2 numbers are closer to A than the upper bound and lower bound in step 2. But these 2 numbers can be further improved if I continue to increase the number of rectangles. Here, in step 4, let me make a table, okay? Let me make a table, okay? The first column, N, is the number of rectangles. Yeah, N is the number of rectangles. Here, this is a typo. This should be rectangle. Second column is Ln. Ln means the sum of the areas of the n rectangles. Those rectangles are built by using function values at the left end points of subintervals as height. And Rn, the third column, Rn is the sum of the areas of the n rectangles. Those rectangles are built by using function values at the right end points of subintervals. Okay. Okay, now when I use when I use 10 rectangles to approximate the region S, the lower bound is this number. Ln is this number. The upper bound is this number. A, the area of the region lies between Ln and Rn, lies between these 2 numbers. Now, if I increase the number of rectangles to 20, from 10 to 20, then the lower bound is this. The lower bound is increasing, but the upper bound is decreasing. And A lies between these 2 numbers. These 2 numbers closer to A than these 2 numbers. continue to increase the number of rectangles. If I let the number of rectangles approach infinity, then I can see that Ln, the lower bound, is increasing to 1/3. And the upper bound, Rn, is decreasing to 1/3. And the exact area of the region always lies between lower bound and upper bound. Okay. So lower bound increase to 1/3, upper bound decrease to 1/3, and A lies between Ln and Rn. Then what is A? A is 1/3. 1/3. So the area, so the region between this parabola and x-axis, and between 0 and 1, the area of this region is 1/3. Low more, low less, 1/3, exactly 1/3. In example 1, we successfully find the area of the region that lies between a parabola and x-axis and between 0 and 1. The solution can be applied to find the area of a region that lies between a general curve and x-axis. Let me make a summary here. Suppose we want to find the area of the region bounded by the graph of some function. This function may not be a parabola, can be a general function. And the x-axis and between A and B. Here is a diagram about the region S, Yeah. This region lies between the graph of some function and x-axis and between A and B. Yeah. I shade the region here. Yeah. Suppose we want to find the area of this region. Now, the solution is similar to this example one. Build rectangles. Step 1, evenly cut the interval AB into n subintervals. And the cutting points, let me name the cutting points. A, the left endpoint of the interval AB, is x0. Just name. Yeah. And then the first cutting point is x1, second cutting point x2, and so on. And B, the last point is xn. Now we have n subintervals. Because we cut the interval evenly, so the length of each subinterval is computable. From A to B, the length is B minus A. Now B minus A is cut into n parts, So B minus A over n divided by n is the length of each subinterval. According to the book used delta x to denote the length of each subinterval. So delta x is B minus A divided by n. Okay, now after we cut the interval AB into n subintervals, now step 2, build rectangles. To build one rectangle, we need a height for that rectangle. Okay. Let's consider the first subinterval. Then for the height of the rectangle, we can arbitrarily pick a point. Say, let me name the point x1 star and use function value and x1 star as the height of the rectangle. Build one rectangle. You can choose x1 star as left endpoint. You can choose x1 star as right endpoint. Or you can choose x1 star at the midpoint of the interval. Or you can arbitrarily pick x1 star. It doesn't matter. Okay. Now, after we have x1 star, we have function value at x1 star. Use the function value as height to build one rectangle. Similarly, over the second subinterval, build one rectangle. Arbitrarily pick upon, say, x2 star. You can pick this point as left endpoint, right endpoint, or midpoint. It doesn't matter. Or arbitrary point. Okay. Now, function value at this point as the height to build one rectangle. Do the same for the remaining subintervals. Build rectangle. Build rectangles. Okay. Now, step 3. Compute areas of the rectangles. Say, the first rectangle area is base times height. Base is the length of the subinterval. It is b minus a divided by n, or delta x. So area of the first rectangle is base delta x times height, function value at x1 star. This is the area of the first rectangle. Area of the second rectangle base, the length of the subinterval delta x times height, function value at x2 star. This is an area of the second rectangle, and so on. Yeah, this is the area of the last rectangle. Base delta x times height, function value at xn star. Okay. Now compute the areas of the rectangles, then make a sum. Make a sum. Yeah, make a sum. Yeah, here there is a shorthand notation for this sum. This is when n, the number of rectangles is large. This sum is a long sum. The book introduced a shorthand notation for this long sum. Okay, the book called this notation sigma notation. Sigma means summation. Yeah, this is a Greek letter. Sigma means summation. The general term, there are many terms. The general term is f xi star times delta x, general term of the left side. Then what is I? I goes from 1 to n. When I is 1, the general term is the first term. When I is 2, the general term is the second term. When I is n, the general term is the last term. So summation, sigma means summation. Summation on the general term with I going from 1 to n. Use this shorthand notation to denote this sum. Yeah. Okay. This sum is sum of the areas of all rectangles. Sum of the areas of all rectangles. This sum roughly is the area of the region S. Not exactly, roughly. Yeah. A roughly is this sum. A means the area of the region S. We want to find A. Yeah. This approximation becomes better and better as the number of the rectangles increases. Okay, now the last step. Okay, we need to determine limit. Okay, a limit. Okay, now let n, the number of rectangles, approach infinity. Then you will see that this sum will approach some number. Yeah, when n approaches infinity, this sum will approach some number. The number is the limit. Okay, and also the number is exactly the area of the region S. So this is a summary, 4 steps to find the area of the region that lies between a general curve and x-axis and between A and B. 4 steps. To find the area of a region between a curve and x-axis and between A and B, there are 4 steps. Some people may say that it is difficult to remember those 4 steps, too tedious. Here, there is a suggestive notation to help you remember the 4 steps. Instead of using A is a letter. It contains only a little information. A just means area. Instead of using A, we use this notation to denote the area of the region. This notation contains a lot of information. In this notation, function f represents the height of a rectangle. Dx represents the base of a rectangle. So f of x times dx is the area of a rectangle. Now, after we have areas of rectangles, we need to sum up the areas. The notation is this. S is the first letter of the word sum. Okay, so sum up areas of the rectangles, sum up areas from A to B. Yeah, this notation means sum up the areas of the rectangles from A to B. After we sum up the areas, we need to take limit. We need to let n approach infinity. Then the sum of the areas will approach some number. The number is the exact area of the region. So we need to take limit. How to represent taking the limit? We elongate the letter S. Okay, elongate the letter S into this symbol. This is an elongated S. We use elongated S to represent taking limit. So we get this notation. So this notation is suggestive. When you look at this notation, you can remember the 4 steps to find area of a region between a curve and x-axis between A and B. Okay, here some terminologies about this notation. The elongated letter S, we call it integral sign. Give a name to it. Give a name to this symbol. We call it an integral sign. The point A, we call it the lower integration limit. B is the upper integration limit. Then how about the function f? The function f, we call it an integrand. And also we give a name to this sum. Okay, this sum is summation of areas of rectangles. Yeah, this sum. We give a name to this sum. We call this sum a Riemann sum. Riemann is the name of a mathematician who generate these 4 steps to find the area of a region. So we name the sum after Riemann. Xi star is an arbitrary point from a subinterval. If you choose Xi star to be the left endpoint of the subinterval, then this sum is called a left Riemann sum. If you choose Xi star to be the right endpoint of the interval, then this sum is called a right Riemann sum. If you choose Xi star as the midpoint of the subinterval, then the sum is a midpoint Riemann sum.